Good day guys, and welcome to the Success Blueprints YouTube channel 247. Please, if you are new to the channel, please do subscribe because this channel will be of great help to you, especially to those of you sitting for your GC examination 2025, being the ordinary level or the advanced level. So today we'll be looking at the Southwest Regional Mock 2025, particularly ordinary level physics paper 2 0580. Now to the left of my screen we have the question paper. This paper was written on Wednesday, the 26th of March 2025, afternoon session. Normally, the paper is designed to be answered in 2 hours 30 minutes. Instructions to candidate. Please always do read the instructions vividly before you answer the questions, because normally the instructions give you a guideline on how to answer the questions. Now, the paper is divided into 2 sections. We have section 1 and section 2. Section 1 is designed to be answered in an hour and section 2 in 1 hour 30 minutes. In section 2, you are supposed to answer either A, B, and C, or D, E, and F of each question. As for the information given to you, we have our value of G. The value of G, the acceleration due to gravity or the acceleration of free fall, G to be 10 meters per second squared. Without wasting much of your time, let's get straight to the questions. Now, section 1, answer all questions as that's always been. Question 1. A glass rod is rubbed with dry cloth. The rod becomes charged and can pick up small pieces of paper. Okay. Roman 1. State the sign of the charge on the glass rod and explain its origin. That's for 2 marks. Roman 2. Explain why the glass rod will not be charged if the cloth is with 2 marks as well. Roman 3. Explain why on taking the charge rod close to the cap of a positively charged gold leaf electroscope, the leaf diverges more. Okay, back to my drawing board. Now, to answer the question, clearly consider the question is coming from electrostatics. And what will I see? Electrostatics is simply that branch of physics that deals with the study of electric charges at rest and the forces, fields, and probably potentials associated with these charges. Normally, it involves understanding how these charged objects interact with each other, the behavior of the electric fields created by this charged object, and probably the potential energy stored in this charged object. That is electrostatics. Now, as far as this notion of charging is concerned, whenever you rub 2 pieces of materials, that is charging by contact. When you rub 2 pieces of materials and it happens that at the end of the day, one of the materials become charged, it means that there must have been the movement of charges from one material to another material. And as we all know, there are 2 types of charges. We have positively charged protons and negatively charged electrons. Take note, there is a movement of charges, yes, but these charges predominantly will be electrons because protons are statics. Protons do not move. Protons do not move, I repeat. So if you rub a glass rod with a dry cloth and it happens that the rod becomes charged, it means that there must be the movement of electrons from the glass rod to the dry cloth. Now, as electrons leave the glass rod, the dry cloth, at the end there will be a deficiency of electrons in the rod, because initially there were equal number of protons and electrons. Electrons leaving out the rod leaves a deficiency behind, so the number of protons in the rod becomes more than the number of electrons. So at the end we are going to see that what the rod becomes positively charged. Question 1. The rod becomes positively charged. Roman 1. The rod becomes positively charged. As for the explanation, as I said earlier, explanation. So the rod becomes positively charged because electrons leave the rod. As electrons leave the rod, the number of protons in the rod outnumber the number of electrons which are left in the rod. So overall, there will be a net positively charge. Okay, so this is because there is the movement of electrons from the glass rod to the dry cloth. Hence, the overall charge on the rod is positive. Now, Roman 2 demands we explain why the glass rod will not be charged if the cloth is weak. Now, one thing is clear here. The wet cloth contains normally water. It contains water. And now, water is a good conductor of electricity because water contains ions. In water, we have the hydrogen ions and the hydroxide ions, OH minus ions and H plus ions. Now, what happens? This wet cloth allows electrons to move freely between the rod and the cloth, and for that reason it prevents effective charge transfer, as any charge that tries to accumulate on the glass rod is immediately being neutralized by the wet cloth. That means at the end of the day, the rod will not be charged if we were to use a wet cloth. Putting this down, I'm going to write, I'll say the wet cloth allows the free movement of electrons between the cloth and the glass rod. As such, it prevents effective charge transfer. As any charge that accumulates on the rod is immediately neutralized by the wet cloth. Hence, the rod will not be charged. Okay. Roman 3 demands, let's explain why on taking the charge rod close to the cap of a positively charged gold leaf electroscope, the leaf diverges more. So in this question, they're just trying to verify your understanding about the fundamental law of electrostatics. And according to the fundamental law, it states that like charges will repel while unlike charges will attract. So bringing a positively charged rod close to a positively charged gold leaf electroscope, there will be repulsion, okay, because the rod is charged positively. The gold leaf electroscope also charged positively. So what do you expect? Repulsion. So as you are bringing closer, there will be repulsion. So if I was writing this down, what I'll say is this. That's Roman 3. The leaf diverges more due to the repulsion between the positively charged glass rod and the positively charged gold leaf electroscope. In accordance to the law of electrostatics, to the fundamental, let's be precise, to the fundamental law of electrostatics. Okay guys, that was all about question 1. Let's proceed to question 2. Now question 2 reads 2a, define density and write down its SI unit of measurement. That's for 2 marks. B, the density of water is 1.0 gram per cm cube. What does it mean? Also 2 marks. C, a 480 gram piece of rock occupies a volume of 30 cm cube. Calculate its density. Now, so without wasting much of your time, let's go straight to the answers. Okay, now I will say that what density is the mass per unit volume of a substance. Density is a mass per unit volume of a substance, and its SI unit of measurement is kilogram per cubic meter. Though you can also measure density in gram per cm cube, okay, but here we are talking about the SI units of measurement, which is kilogram per cubic meter. Now B, in B, we have been told the density of water is 1.0 gram per cm cube. What does this mean? Normally we are talking about 1 gram per cm cube. It means that what? This simply means that 1 gram of water, the mass of 1 gram of water occupies a volume of 1 cm cube. Okay, so if we should take 1 cm cube of water and we measure the mass of that 1 cm cube, that will be equivalent to 1 gram. So writing this down, I will say a density of 1.0 gram per cm cube simply means simply means 1.0 gram of water occupies a volume of 1 cubic centimeters. Now C says a 480 gram piece of rock occupies a volume of 30 cm cube. Calculate its density. Now, okay, so the parameters given to us, or the given information, we have been given the mass to be 480 grams. We have been given the volume to be 30 cm cube. Now what do? We know that what density, denoted rho, is the mass per unit volume. So keying these parameters into this formula, we're going to have that density will be equal to, sorry, this was 480, not 48, 480 grams. So we're going to have 480 grams divided by 30 cm cube. This boils down to, if you quickly punch, you are going to have the density to be equal to 16 gram per cm cube. Take note, you can keep your answer like this, or you can as well convert to the SI unit, which is kilogram per meter cube. That means you divide by 1,000 and you multiply by 1,000,000. Okay, now that said, let's move over to question 3. Now question 3 reads, that's 3A, state 2 ways by which waves can be classified. Okay, that's for 2 marks. And B, figure 1 shows a displacement time graph traced by a signal generator. Roman 1, calculate the frequency of the knot for 2 marks. Roman 2, sketch the trace for a knot of pitch twice that in figure 1, that is the amplitude being constant. Okay, so now talking about waves, I will say waves are normally classified into 3 categories. Okay, we have waves can be classified based on their speed in air or vacuum. Waves can be classified based on their means of transferring energy, and waves can be classified based on their mode of propagation. That's what you should know. Waves can be classified based on their speed in air or vacuum, based on their mode of propagation, and based on their means of transferring energy. Okay, now based on speed in air or vacuum, waves can be classified into 3. We have mechanical waves, we have electromagnetic waves, and we have matter waves. Based on their mode of propagation, waves can be classified into 2. We have longitudinal waves and we have transverse waves. And lastly, based on their means of transferring energy, waves can also be classified into 2. We have stationary or standing waves, and we have progressive waves. So as far as this question is concerned, you are supposed to pick any 2 of your choice out of the 3 different classification methods or schemes. You pick any 2 from there and you give. So I'll just give the 3. It's your choice to pick 2 from there. So I'll say classification of waves. So I'll say waves, classification of waves. Classification of waves. As I said, waves can be classified based on one condition. They can be classified based on their speed in air or vacuum. And under this classification, we have three classes of waves. 1, we have mechanical waves, which are waves produced by the vibration of matter, and they require material medium for their transfer. 2, we have electromagnetic waves, which are waves that do not require material medium for their transfer. In fact, they can travel through vacuum with the speed of light. And lastly, we have matter waves. Normally, these are waves associated with fundamental particles like electrons. Okay, now the second scheme of classification, we have waves can be classified based on their mode of propagation. Here we have 2 classes of waves. Here we have longitudinal waves, which are waves that the vibrations of the particles of the medium are parallel to the direction in which the wave is traveling or propagating. Secondly, we have transverse waves. which are waves in which the vibrations of the particles to the medium are perpendicular or normal to the direction in which the wave is traveling. And lastly, waves can also be classified based on their means of transferring energy. Means of transferring energy. Here, as I said, we have two classes. We have standing waves, which are waves produced whenever two progressive waves meet, either in phase or out of phase. Now, in these standing waves, we have regions of maximum displacement called antinaught and regions of minimum displacement called naught. And lastly, we have progressive waves. These are waves in which the speed of the wave is in the same direction as the direction in which the wave is traveling, and here 2 points in phase have the same amplitude, unlike in standing waves where there are regions of maximum displacement and minimum displacement called antinaught and naught respectively. So this is the classification of waves. You pick any two from here, you pick any two modes, that is classes of waves, and then you give it. Now, that was question 3, not 4. Okay, sorry for that. That was question 3. That was 3E. Now in B we have this progressive wave profile, a diagram of displacement in centimeters against time in seconds. Now it says calculate the frequency of the knot and sketch the trace for a knot of pitch twice that in figure 1, that is amplitude being constant. Okay, now the very first thing I'll need to do here is to draw a diagram. So I'll just pause the video and sketch the diagram, and then we'll continue from there after. Okay guys, so that's the diagram of the wave profile. It wasn't clear enough, so I just suppose these values I've indicated here, 8 and -8, they are the values on the diagram. It's not clear enough. We'll just manage this. Okay, so we have our displacement time graph, our displacement against time graph. So from this graph, what we can get from the graph, we can get the amplitude of the wave and equally the period, because we cannot get the frequency directly from the graph. So if I was to indicate quickly, I will have this distance from here to here to represent my amplitude. This is my amplitude. And the time taken from this point obviously is 0 up to this point is the period. So let's indicate it with capital T. So as far as this wave profile is concerned, if we are to count the number of cycles, we have that from here. From here, this is 1 cycle and a half. Okay, so if that's a cycle and a half, so we can see that what number of cycles n is equal to 1.5. The time taken, total time taken, T is equal to 0.1 seconds. Now, what is frequency? We have that frequency is the number of complete cycles per second. But in this, as far as the diagram is concerned, we have 1.5 cycles in 0.1 seconds. So if we have to calculate the frequency, we have the formula frequency denoted F is equal to number of cycles per unit time. Okay, so in this case, we're going to have our frequency to be equals to 1.5 divided by 0.1 seconds. If you punch a calculator, you are going to have 1.5 divided by 0.1, which gives us 15. Now Roman 2 demands that we sketch the trace for a knot of pitch twice that in figure 1, amplitude being constant. Now one thing you should note here is this: there are three characteristics of sound. We have pitch, we have loudness, and we have timbre. Pitch depends on frequency, loudness depends on amplitude, whereas timbre depends on the type of musical instrument you are using. Now, according to the relationship that exists between pitch and frequency, it is a direct relation. That means an increase in the frequency of a musical note generally leads to an increase in its pitch, as well as a decrease leads to a decrease in pitch. What about loudness and amplitude? It's also a direct relationship. An increase in the amplitude of a musical note leads to an increase in its loudness, as well as a decrease in the amplitude will lead to a decrease in the loudness. Now, timbre, or also known as quality, does not depend on frequency, nor does it depend on amplitude. Timbre depends predominantly on the type of instrument used. You can have two musical instruments producing sound of the same frequency, sound of the same amplitude, but they are totally different. For example, you have a piano or a violin, you can have a guitar or a drum. These different instruments have their respective way, or that is, have their respective melody in which they produce the sound. Okay, now, so if we were to answer this question, since we have to sketch a trace for a knot of pitch twice that in figure 1, it means that what? If the knot is twice, that means the frequency is also twice. So we say since pitch is directly proportional to frequency, it means that for a knot of pitch, twice that in the figure, its frequency F1C will be equals to twice the original frequency. So we're going to have 2 times 15 Hertz, which boils down to 30 Hertz. Now from frequency equals to 1 over period, it means that the period will be equals to 1 over the frequency. This will reduce, this we are going to have 1 divided by 30 Hertz, and this will give us, if you quickly punch, you have 1 on 30, that gives us approximately 0.033 seconds. That is to 2 decimal places. Now, if we have the new period T1C of value 0.033 seconds, the diagram will be as such, wherein the amplitude remains the same. This was a graph of displacement in meters against time in seconds. Okay, so the amplitude remains the same. This will be the amplitude, it remains the same. But as for the frequency, as for the period, this period will become 0.033 seconds. Okay, so that's what we are going to have for this case. Now, the next question 4. It reads, an object of mass 20 kilograms is dropped from a height of 2.6 meters above the ground. Okay. Roman 1, state the law of conservation of energy. That's for 2 marks. Roman 2, what type of energy does the object possess at this height? For 1 mark. Roman 3, as the object falls to the ground, its energy conserved. You should explain. And Roman 4, calculate the final speed with which it hits the ground. Okay, so that is question 4, Roman 1. Now the law of conservation of energy states that what? In any closed system, the total amount of energy is constant. In other words, you can say that what? Energy can neither be created nor destroyed, but can be changed or transformed from one form to another. Writing this down, we see the law of conservation of energy states that energy can neither be created nor destroyed, but can be changed from one form to another. Take note, to change energy from one form to another, we need devices called transducers. Now, Roman 2 demands that we state the type of energy that the object possesses at that height. Now, since we are at a certain height, the type of the energy possessed by the object at that height will be the gravitational potential energy. Normally, there are 3 types of potential energy. We have the gravitational potential energy, we have the electric potential energy, and we have the elastic potential energy. All these forms of energy depends on the type of field. Okay, when we are in the gravitational field, like in this case, we have the gravitational potential energy. When we are in an electric field, we have the electric potential energy. And when we are dealing with stretched objects like rubber bands, we have elastic potential energy. Take note, for the electric or gravitational, it all depends on the position of the object in the field. And in this case, the object is at a certain height. So I will say gravitational potential energy, also known as GPE. Let me write it in capital letters. So we have GPE. Now Roman 3. It says, is energy conserved as a ball or the object falls downward. Okay, now what I will say is this: in a practical situation, energy is not conserved. Okay, energy is not conserved in a practical situation because as the object falls down, that gravitational potential energy is converted not only to kinetic energy but other forms of energy like heat due to friction between the object and air molecules. You can convert it to heat and sound again as the object collides with the ground. Okay, so in general, what I'll write is this: generally, in a practical situation, energy is not conserved since part of the gravitational potential energy might be converted to heat due to friction between the object and air molecules. Also, we have sound upon collision with the ground. Upon collision with the ground. So theoretically, we assume that it is conserved, but in a particular situation, energy is not conserved. Now, Roman 4. In Roman 4, it says, it demands that let's calculate the final speed with which it hit the ground. So here, by the principle of conservation of mechanical energy, by the principle of conservation of mechanical energy, we have that what? The loss in gravitational potential energy is compensated for by a gain in kinetic energy. Now let's sketch a small diagram. Let's suppose that this object was at a certain height here. Okay, now at this height, the object possesses gravitational potential energy, while its kinetic energy is equals to 0 since it is at rest. Okay, now when falling, what happens? As it falls down to a certain height h given to us, as it falls down, this is the ground level. As it falls down, what happens? There is a change in gravitational potential energy. There's a loss in gravitational potential energy because as the ball is descending, what happens? There is a decrease in the height. There is a decrease in this height. So whenever there's a decrease in height, there's a loss in GPE. As the ball finally reaches this point down here, what happened? This is gravitational potential energy that was initially maximum C at this point up here becomes 0 at this point, while its kinetic energy becomes maximum. So Ke will be equal to Ke max. Okay, so now from here we're going to say that what? The change in GPE will also be equal to a change in Ke. Is that okay? So initial GPE is maximum, final GPE is 0. Initial Ke is 0, final Ke is maximum. So in this case, we are going to see that what? Mg change in height will be equal to a half m times the change in velocity, all this squared, where the change in height, we're going to have mg change in height is the initial height minus the final height when it finally arrives the ground level. Okay, while the change in velocity will be a half the final velocity, which is v squared, minus the initial velocity, which is in this case 0, minus initial velocity, which is 0, so squared. So if that's the case, we are going to have this mass first of all cancelling out on both sides, and that means from here we're going to have that GH will be equal to a half v squared, which reduces to v being equals to the square root of 2gh. Now wait, if you go back to the diagram, to the equation, they gave the height h is 2.6 meters, and the value of g that was given to us was 10 meters per second squared. So with h being equal to that and g being equal to 10 meters per second squared, it means that the velocity becomes 2 times this 10 meters per second squared times 2.6 meters. If you quickly punch a calculator, you're going to have that velocity to be equals to, let me punch, we have you're going to have that velocity to be 7.21 meters per second. This is to 2 decimal places, and that is the velocity with which it hits the ground. Okay, now moving over to question 5. Now question 5 says a Form 4 student calibrated a liquid in glass thermometer and found out that the upper fixed point corresponded to a length of 45 centimeters and a lower fixed point corresponded to a length of 5 centimeters. A. Define the underlying phrases. That's for 2 marks. B. State the corresponding standard temperature of the lower and upper fixed points. 2 marks as well. And C. The student measured the temperature of warm water and it corresponded to a length of 25 centimeters. Calculate the temperature of the warm water. Okay, so question 5. What I'll say is this: there are normally 3 different temperature points, okay, known as fixed points. We have the lower fixed point, also known as the ice point, the upper fixed point, also known as the steam point, and the triple point. Generally, the lower fixed point is a temperature of pure melting ice at standard atmospheric pressure. The upper fixed point, also known as the steam point, is a temperature of steam from pure boiling water at standard atmospheric temperature and pressure still. And lastly, triple point. This triple point only applies to distilled water. It is used only in the case of distilled water. It is normally the temperature at which saturated water vapor, pure water, and pure melting ice are all at equilibrium. Okay, so if I was to write this down, what will I say? I'll say A, the first thing, which is the upper fixed point. Take note, also known as the steam point. As I said, also known as the steam point. It is the temperature of steam from pure boiling water at standard atmospheric pressure. Okay, that's it. Next, we have the lower fixed point. As I said, it's also known as the ice point, and it is the temperature of pure melting ice, also at standard atmospheric pressure. Okay, that's it. Now 2, that's Roman 2. Roman 2 says state the corresponding standard temperature of the lower and upper fixed points. Okay, so for the lower fixed point, that is B, for the lower fixed point, the temperature is 0 degrees Celsius. That is according to the centigrade scale, and in terms of Kelvin, it is 273 Kelvin, because to convert from degrees Celsius to Kelvin, you simply add 273. And that's the first one. Also for the upper fixed point, the temperature will be the temperature is normally 100 degrees Celsius, which in Kelvin will be 373 Kelvin. So these are the values at lower and upper fixed point. Next is the amount that we calculate temperature of warm water. Now look up, take note. Different thermometers exist. Okay, these thermometers are differentiated by their thermometric property, a physical parameter that varies linearly with temperature and it is reducible. That is thermometric property. Okay, now so we have examples of thermometers. We have the liquid in glass thermometer like that given here. We have a constant volume gas thermometer. We have a bimetallic strip thermometer. We have a thermocouple thermometer. We have an electrical resistance thermometer. These are all thermometers that exist, and many others. These thermometers so differentiate themselves based on their thermometric property. So generally, the temperature of a body at any given time based on the thermometric property of a material, theta, is defined by or is given by x theta minus x0 divided by x100 minus x0. Now if we are measuring in the Celsius scale, we are going to multiply by 100 degrees Celsius, where x theta is the thermometric property of that thermometer at an unknown temperature theta. X0 is the thermometric property of that thermometer at the lower fixed point. X100 is the thermometric property of that thermometer at the upper fixed point. So in this case, for a liquid in glass thermometer, this particular equation, which is for all types of thermometers, will transform. It will become theta being equals to L theta minus L0 divided by L100 minus L0 times 100 degrees Celsius. Why is this so? Because for a liquid in glass thermometer, its thermometric property is the length of the liquid column. Okay, so that's why we change it to L, because X here, as I said, is just a general parameter depending on the type of thermometer. For a liquid in glass thermometer, we change it to the length, which is a thermometric property. So according to the equation, it says the length of the upper fixed point is 45, the lower fixed point is 5, and at an unknown temperature the length is 25 centimeters. Okay, so we have the parameters given to us. So we have parameters. Please always do copy your information. So we have L theta is given to be 25 centimeters, L0 is given to be 5 centimeters, and L100 is given to be 45 centimeters. With all of these, you are going to have theta will be equals to, if you key in the values quickly, we're going to have 45 centimeters minus 5 centimeters divided by 25 centimeters minus that same 5 centimeters multiplied by 100 degrees Celsius. This will quickly reduce to theta being equals to 40 on 20 times 100 degrees Celsius. Centimeters will cancel out, and this will give us 200. I've made an error. This was supposed to be the reverse. Sorry for that mistake. This is supposed to be the reverse. This is supposed to be 25 up minus 5 centimeters divided by 45 centimeters minus 5 centimeters. Okay, so this will give us 20 over 45, which theta boils down to 20 on 45 is 0.5 times 100. That will give us 50 degrees Celsius. So the temperature of that warm water, the temperature of the warm water will be 50 degrees Celsius. Now let's proceed to question 6. Question 6 says the figure below shows a ray of light moving from air to glass. Okay, that's our diagram. A ray of light moving from air to glass. Roman 1. Name the phenomenon that occurs as the light travels from air to glass. For 1 mark. Roman 2. What is the angle of incidence I? What is the value of the angle A? And Roman 4. Calculate the refractive index of the glass. So let me quickly represent the diagram. Okay guys, so this is the diagram wherein this normally is supposed to be our normal. This is our incident ray. This this is our refracted ray. Okay, now according to the diagram, this angle here, if I see very well, this angle here is 40 degrees. This one here is 35 degrees. This here is A, and this is I. Okay, now I suppose those angles I've indicated there as on the diagram. Now A, name the phenomenon that occurs as the light travels from air to glass. Quickly, if you are a smart student, you discover what? Since they say it is a refracted ray, that means possibly it is refraction. That was a quick one. That was a quick one to easily get. So that is question 6. A. Question 6. Roman 1. Sorry. Question 6, Roman 1. So quickly, I'll say the phenomenon is refraction. Now, my dear friends, what is refraction, or why is it refraction? It is refraction because there's a change in the medium. Okay, there's a change in media. Since the ray is initially traveling in air and it gets into glass, that is a change in media. Okay, so it is refraction. So refraction is generally that phenomenon of a wave, particularly in light, wherein the path of a light ray changes direction as it changes from one medium to another medium. Okay, that's it. So Roman 2, it asks, let's calculate the value of the incidence angle I. Now if you look at the diagram clearly, you see that what this angle here is supposed to be 90 degrees. This value here is 90 degrees. So if it is 90 degrees, since I and 40 degrees make 90, I'll say that what I plus 40 degrees will be equals to 90 degrees, which quickly I will be equals to 90 degrees minus 40 degrees, which boils down to 50 degrees. That is the angle of incidence. In Roman 3, we are going to apply a similar trick to get the value of A. Now if we go to the diagram, back to the diagram, this angle, this total angle here is 90. That means also this one normally is also 90. Now if it is 90, it means that there is a certain angle here that we must get so that we can add this 35 degrees, the value of A, and that angle to get the value of A. And we'll add all of them, we equate to 90. So let's suppose this angle here is X. Now if you look clearly, if you look very well, this 45 degrees will also correspond to this angle. Opposite vertical angles are always the same. So clearly from the diagram, we see that what? So I'll say from the diagram, the value of X is equals to, X will be equals to 40 degrees. Okay, 40 degrees. Since opposite vertical angles are the same. Opposite vertical angles are the same. Now with this value of x, I'll have that what? 35 degrees plus a plus that value of x, which is 40 degrees, must sum up to 90 degrees. The right triangle, the right angle, this angle here, must sum up to 90 degrees. From here, 35 plus 40 gives us 75 degrees. So our plus a will be equals 90 degrees, which means that a will be equals 90 minus 75 degrees, which gives us 15 degrees, and that is the value of E. Roman 4. Calculate the refractive index of the glass. Okay, so here we are going to apply Snell's law. Okay, Roman 4, we are going to apply Snell's law. Now say from Snell's law, the sine of the angle of incidence to the sine of the angle of refraction must be equal to a constant, normally called the refractive index. This is for any ray of light traveling from one medium to another. Okay, so with R equals to, from the diagram, the angle of refraction. In the diagram, the angle of refraction is this angle, the angle to which the refracted ray makes with the normal. The angle of refraction is 35 degrees. So from the diagram, R is equal to 35 degrees. With that value of R, I'll have N to be equal to sine of the angle of incidence. We should show that the value of incidence is 50. So I'll have sine 50 degrees divided by sine 35 degrees will give us the value of N. If you quickly punch, you have that refractive index of glass to be equals to, we have sine 50 divided by sine 35 degrees. That gives us 1.34 degrees. This is two decimal places. So normally the value, the refractive index of glass ranges between 1.5 to 1.55. Okay, so probably maybe there's this angle that we didn't see very well, but I suppose it is 35 degrees, and if it is 35 degrees, then this will be our refractive index. Okay, to question 7. Now question 7 is under section 2. Okay, so as the instructions were very clear, they say you can either answer A, B, and C, or you answer D, E, and F of each question. Now question 7a, it reads: a student given an ammeter, a voltmeter, and a battery was asked to measure the resistance of a copper wire. Roman 1. Draw a labeled diagram of the circuit he will use. That's for 2 marks. Roman 2. He noticed that varying the battery's voltage causes the readings on the ammeter and the voltmeter to change. State the law linking the readings of the ammeter and the voltmeter. For 2 marks. In Roman 3, the following readings were obtained. So our values of voltage against values of current, probably from the voltmeter and the ammeter. Draw a graph of voltage against current. That's for 5 marks. Roman 4. From your graph, state with a reason whether the copper wire obeys the law you stated in Roman 2 here or not. And 5. Use your graph to determine the resistance of the copper wire. Okay, so we have section 2. We have section 2, question 7. Now, drawing a circuit diagram that has an ammeter, a voltmeter, and our copper wire with a battery depends. Here, in fact, they are just trying to evaluate how good you can know how these devices are connected in a circuit. Now, take note, an ammeter is always connected in series to the circuit component whose current is to be measured. A voltmeter connected in parallel to the circuit components whose voltage is to be measured. Now, a property of the ammeter that necessitates it to be connected as such is because of its low resistance, so as not to alter the current flow in that circuit. Okay, whereas for the voltmeter, if it must measure the voltage drop across a circuit component, then it must have a very high resistance so as not to absorb current from the circuit. Okay, so if that's the case, we are going to have this diagram. Let's suppose we have this diagram. We have our battery. Okay, that is the circuit symbol for a battery. With that battery, we are going to have probably our ammeter here, always noted A, in series. Let's suppose that this is our copper wire. This is our copper wire whose current and voltages are to be measured. Now, let's complete circuit. As for the voltmeter will always be in parallel. Okay, so the voltmeter, if I also indicate it, I'll put the voltmeter here in parallel. This voltmeter measures voltage drop across our copper wire of resistance R, while the ammeter measures the current that flows in the circuit I. So this is our battery. If we must level, this is our voltmeter, and this is our ammeter. Not forgetting, this is the copper wire. Okay, so that will be a simple circuit that we can mount to get the value of voltage and current in the circuit. Okay, now B, not B, that is, B was A Roman 1, A Roman 2. Okay, now for A Roman 2, it says, let's take the law linking the readings of the ammeter and the voltmeter. The ammeter measures current, the voltmeter measures voltage, and this law will normally be Ohm's law. Okay, Ohm's law. This law states that the current I flowing through any ohmic conductor is directly proportional to the potential difference drop across that conductor, provided physical conditions like what? Temperature, like length of the conductor, like the cross-sectional area of the material are kept constant. So I is directly proportional to V. This normally always boils down to V equals to IR. Take note of that. Now Roman 3. In Roman 3, we are to sketch a graph. So the very first thing I'll do is this. I'll recover back my table, okay? And from there now we analyze how we are going to sketch a graph, looking for the scale, labeling our axis, and many other things that we'll look at. So let me quickly get my values, my table of values. So I have this. I'll have a table as such. Always copy a table again into your answer sheet. So we have our table. We have values of V in volts and values of I in amperes. We have 0 against 0. We have 1.0 against 0.12. We have 1.6 against 0.2. We have 3.7 against 0.4. We have 4.8 against 0.6. We have 6.0 against 0.75, and lastly we have 8.0 against 1.0. So this is our table of values. Okay, so as for the graph, we'll look at the analysis of the graph. I will do a video where we'll look at the analysis of the graph.